If you drop a Lego spaceship onto a hard floor, it shatters into its component parts. By weighing those individual pieces, a thruster here, a wing panel there, you can determine the original structure of the ship. Mass spectrometry applies this same logic to molecules. This graph shows the result of that process for a molecule of ethanol. The x-axis, labeled m/z, represents the mass of each fragment. The y-axis shows the relative abundance, or how many of those specific fragments successfully reach the detector. To identify the original molecule, we look for the peak with the highest mass on the far right. This is the parent ion. It represents the total molecular weight of the ethanol before it was broken apart, in this case, 46. The tallest peak on the graph is called the base peak. It represents the most common fragment created during the process. While the parent ion tells us the total weight, the base peak shows us the most stable way the molecule breaks. We can identify what the molecule is made of by looking at the gaps. If we calculate the difference between the parent ion at 46 and the base peak at 31, we find a loss of exactly 15 mass units. Losing a mass of 15 means the molecule dropped a methyl group. Only pieces retaining a positive charge are steered to the detector. The uncharged methyl group vanishes invisibly. The remaining charged fragment, weighing 31, hits the detector, creating our signature base peak. Molecules break at specific weak points to form the most stable fragments possible. In mass spectrometry, stability describes how well a fragment can support its positive charge. The more stable a fragment is, the more likely it is to survive the journey to the detector, and the taller its peak will be. Take N-heptanol. The parent peak at 114 represents total mass. A prominent fragment sits at 85. Pause the video and subtract. What neutral piece broke off? 114 minus 85 is 29, a 2-carbon ethyl group. Losing it forms the 85 fragment. These two molecules are isomers. They contain the same number of atoms and have the exact same total weight. However, their physical structures cause them to shatter in very different ways. This spectrum shows a very weak parent ion, but a massive base peak at 57. This suggests the molecule is highly prone to breaking and forms one specific, extremely stable fragment. This indicates a branched structure. In a branched molecule, the charge can be shared across multiple carbon neighbors, which makes the fragment much more stable. When this molecule snaps at this branch point, it creates a 4-carbon cluster called a tert-butyl group. Because that cluster weighs 57 and is highly stable, it produces the dominant peak we see here. You can navigate most spectra using 3 steps. Find the parent ion for the total mass, find the base peak for the most stable fragment, and subtract the two to find the mass of the neutral loss. You don't have to identify every minor signal on the graph. By focusing on the parent weight, the tallest peak, and the mass of the major fragments, you can determine the identity of the original molecule.